Let's just move on to mixtures. All right, mixtures, that's the other half of our chart up here. Remember, we had matter, and then over here were the pure substances, and over here we're now in the other half, which is the mixtures. So, what is a mixture? We're now on the second page of the guided notes. Mixture is matter that consists of two or more substances together that are not chemically combined. Okay, so while we were talking about, a compound that was CO2, right? These are two substances, carbon and oxygen, but they exist together in one molecule. A molecule of carbon dioxide kind of looks like this. Okay, they are chemically combined via these chemical bonds. A mixture is stuff that's floating around next to each other or maybe combined into the same solid, but they're not bound to each other chemically. Okay, so an example here, we've got, this is, for example, what a water molecule looks like with the two hydrogens coming off of it and then a bigger oxygen in the middle. So that's a compound, and we've got more of them around over here. And this is a completely different compound. They exist together, but they're not bonded to one another. You can see these are not touching each other, these two compounds. Okay, so that would be a mixture. Okay, and this is the same example, except this is just one element by itself and a different compound, but once again, these are not touching each other because they're not chemically bonded, and so this would be a mixture. And these are two more diatomic elements. Remember, those were the things like hydrogen or oxygen that where two of the elements, two atoms are put together to make one molecule. So the point being, you put them together, but they are not bonded to one another. That's what defines a mixture. So, substances in a mixture keep their separate identities and most of their own properties. So, example here, right? This is a extremely basic mixture, right? It's just, we've got pasta, which is a combination of a whole bunch of things. It's itself kind of a mixture, and then you're just putting it in a pot of water and maybe some salt in there. But if you were to separate the salt out of this, it would still taste like salt. Like, this mixture would taste salty. The water would still be wet and boil at the same temperature, etc. And then pasta, if you took one of those noodles out and ate it, it would taste like raw pasta, right? These did not change just because you put them together in a mixture. Another example would be lemon juice. There's water in there. The lemon juice, it still, tastes sour. And the sugar, that's what this is sucrose, would still be sweet. They may change in physical appearance when they dissolve. For example, when you dissolve sugar in water, it goes from, this white powder, crystalline stuff, and then when you dissolve it, it disappears essentially. It becomes clear because it's dissolved in the water. Some properties can also change, such as melting point or boiling point. For example, if you take water, add a bunch of salt, and then try to boil it, it'll boil at a higher temperature. That's why, for example, this also applies to a melting point. That's why people put salt on the roads when it snows. It helps it melt at a lower temperature. But it does not change the chemical composition. So, chemical composition in your notes there. Substances in a mixture can be present in any amount. So, if you're making salsa here, which is another example of a mixture, it could be like 99% tomato with just one tiny bit of onion and one bit of pepper in there, or you can swap it all around. It wouldn't change the fact that it's a mixture, and it wouldn't change the fact that it's salsa, although it might be less desirable salsa if you don't do it in the right ratios. Mixtures can be separated out by physical means. Okay, so what does that mean? We'll go over in our next video physical properties, but basically you don't need to do anything chemically to a mixture to get the component parts back out. Okay, going back to our pasta and our salt water example, to get the pasta out of there, you can, reach in there with a pair of tongs and pull out the pasta. And then to get the salt back out, you could evaporate off the water, which is a physical change, and then the salt would be still in there, sort of sticking to the bottom of the pan. Okay, so these are examples of physical changes that you can do to separate out a mixture, such as sorting things out, sifting, like if you have a bunch of gravel and you're sifting it to get out the dirt, or evaporation, as I just mentioned, to get the salt out of salt water. Okay, there are two types of mixtures. There's heterogeneous mixtures and homogeneous mixtures. Okay, let's start with a heterogeneous mixture. The difference between these is kind of, it's not super scientific, it's more kind of just based on how it presents, what it looks like. Okay, heterogeneous, hetero means like different or opposite. It just means a mixture that doesn't seem to be all made of the same thing when you look at it. So this is an example. It's a fruit salad. You can see there's pineapple, grape, strawberry, blueberry, some cantaloupe in there. If you sort of picked any individual thing out of it, it would look different, and that's what being a heterogeneous mixture means. Some examples, such as this salad dressing here, may, if you kind of shake it up and emulsify it, like you often do before using salad dressing, it'll mix up and it'll kind of seem uniform and therefore homogeneous, but if you leave it sitting on the counter for a long time, it'll separate out into having a sort of a top layer that's, which goes on top. Like vinegar will usually be the top layer, and then oil will be on the bottom. Okay, and so it will become heterogeneous even though it seems homogeneous when you've kind of mixed it up together. Alright, and there's some pictures that illustrate that. And the reason it does this, by the way, is because the oil is literally heavier than the vinegar, which is mostly water. Okay, homogeneous mixtures, that's the other type. It's a mixture that appears to be the same throughout. These are also called solutions. In fact, almost no one ever refers to a homogeneous mixture. And the particles, unlike heterogeneous mixtures like the salad dressing, a homogeneous mixture such as salt water would never the particles would never settle out if you just leave the mixture sitting there. You would never have a thing where you have a cup full of salt water, and then if you leave it there for a while, a bunch of salt crystals start forming at the bottom. If they're dissolved, as long as nothing else changes. So an example of this would be coffee. No matter where you look in this cup of coffee, assuming you've filtered out all the grounds and stuff like that, it all would just look like coffee, right? Perfume, another example. Metal alloys are another example of this. So if you look at these different types of gold or silver, no matter what sort of chunk you pull out of these rings, they're all going to appear to be the same. Talking more about solutions, we've got a solvent. Solutions are made of two things, a solvent and a solute. Okay, solvent is the substance that the solute dissolves in. Okay, so if we're talking about salt water, okay, the thing that the solute dissolves in, aka the thing we use to dissolve the other thing, is the water in this case, right? In fact, water is referred to generally as the universal solvent. And then the salt is the solute, that's the particle that is dissolving. we dissolved the salt in the water, so the salt is the solute, and the water is the solvent. This is just some vocab to remember. We will talk about solutions all throughout the semester, and especially in the chemistry part. So, just bits to remember. Yeah, and the substances making up the solution retain most of their original properties. As we've said before, salt water, if you drink it, it tastes salty because there's salt in there. It doesn't taste sweet because the salt has somehow changed by being dissolved. No, it still behaves more or less like salt. Importantly, solutions can exist in any of the three states of matter. We mostly talk about solutes and solvents in terms of a solid or liquid being dissolved in another liquid, but like we were talking about, the metal alloys, those can exist, those are solid unless you melt them. Those are also technically solutions because they are homogeneous mixtures. Okay, and an example of a gaseous, so that's the third state of matter, an example of a gaseous homogeneous mixture is air. Okay, air, the air that we're breathing right now, is made up mostly of nitrogen, but there's also oxygen, crucially, for us to survive. There's hydrogen, there's helium, there's other stuff like argon, kind of more interesting gases in there. So these are all mixed together, but if you took any kind of sample of air and looked at it, it would look the same as any other bit of air that you looked at. And so crucially, that is what makes it homogeneous and a mixture. Okay, that was a long set of notes. We're probably going to cut that in half. Now would be a good time to check and make sure you filled in all the blanks on your guided notes. Okay? All right, I will see you in class.